In this part of my presentation, I will share with you the results of my group on EEG activity in persons with high cognitive and motor performances. It's well known that persons with special skills and abilities have special features of brain activity during this cognitive task or exercise. And it's called neural efficiency, the features of brain activity showing selected involvement of brain areas during the high performances in cognitive tasks. This neural efficiency, which appears to be more selective brain activation in experts in comparison with people with normal performance. This neural efficiency was observed in persons with a high intelligence quotient, or also people with special skills in, for example, in musicians with a high performance in the music field. And also there are some experiments on neural efficiency in heartless, considered as experts in some fields of cognitive and motor tasks, the sporting activity. So my group developed some experiments in Atlas of several disciplines to test the hypothesis of neural efficiency in these people. And we started with the recording of EEG activity in the resting state, eyes closed and eyes open condition. As you can remember, this resting state condition is especially useful to investigate the neural correlates of the systems adapting the vigilance level and brain arousal during wakefulness. So it's expected that the neural efficiency, so selected brain activity was related to some special features of resting state, e.g. alpha RIMS, which are related to cortical inhibition during quiet wakefulness. And the experiment was performed in elite karate athletes, amateur karate athletes, and non-athletes, people not involved in sporting activity at agonistic level. And the elite karate athletes were enrolled from the Italian team of karate. You see at the center of the figure the results at the group level of the cortical sources of electroencephalographic alpha rhythm. You see that you have three maps, and they represent the cortical model of Iloretta software to estimate the cortical sources of EEG activity, nose up. Red in the cortical model means high source activity. You see that the upper map reports the results of elite karate athletes, and it's very clear the significant cortical source activity of alpha resting state rhythms. The localization was on posterior parietal occipital cortical areas and some posterior midline and central midline. So you see in the map in the middle that the alpha source activity was present, but with less activation in amateur karate athletes. So people involved in training of karate, but at amateur level. And you see that the non-athletes show a pattern of alpha source activity similar to amateur karate athletes. So the results show that in comparison with amateur karate athletes and non-athletes, the elite karate athletes were characterized by higher alpha source activity in the resting state, eyes closed. So you know that the high EG alpha activity during resting state, eyes closed, means cortical inhibition related to deprivation of visual stimuli and psychophysical relaxation. So the high alpha source activity in athletes in comparison with the control persons showed that in athletes there is a specific background cortical inhibition in quiet wakefulness, ability to inhibit the cortical arousal, the cortical tone in quiet vigilance. And so these results are in line with the neural efficiency hypothesis in athletes. The second experiment was performed in athletes to test the hypothesis of high opening reactivity of electroencephalographic alpha rhythms. It's expected that the cortical activation related to visual information processing during eyes open is reduced in athletes in relation to neural efficiency hypothesis. And so we performed the experiment in 28 elite karate athletes and 18 non-athletes. You see that the condition was characterized by the quiet vigilance, a resting state, eyes closed for a few minutes, and then opening the eyes for a few minutes. And so in the eyes closed condition, you expect ample EG alpha rims as a reflection of cortical inhibition. And then with the eyes open condition, the inflow of visual stimuli and some visual information processing in the cerebral cortex, in the visual and visual spatial cortical areas. And so a reduction of alpha rims. This ratio between alpha activity during eyes closed and the percentage reduction of alpha activity during eyes open in the resting state is called event-related desynchronization of alpha activity from eyes closed to eyes open condition. And you see in the maps that we represented the alpha reduction in power from eyes closed to eyes open condition with a red and white. And you see that in the maps, minus 80% of alpha activity was coded by white and red. These maps show nose down. So you see that the upper part of the maps are in the occipital scalp regions. And so you see that in non-atlas, you see a very widespread reduction of alpha activity, the alpha event-related desynchronization, showing that when these people open the eyes, large areas of the cerebral cortex were involved in visual, spatial, and motor transformations. In the lower map, you see the results of alpha event-related desynchronization in karate atlas, elite karate atlas. And you see that the red showing event-related desynchronization is circumscribed in the posterior scalp regions. So we concluded that the reduction of alpha rims from eyes closed to eyes condition was associated with a very widespread and strong reduction in amplitude in non-atlas, and only a moderate reduction in alpha activity in karate atlas. So the reduction of alpha rims reflect cortical activation during visual information processing. And this reactivity of alpha rims, this cortical excitation of during visual information processes was higher in non-atlas. And this confirms the hypothesis of neural less cortical activation in Atlas. So we can conclude that in the experiments on resting state EEG activity showed the confirmation of neural efficiency hypothesis in a heartless brain for the higher function of vigilance control. You see that in the picture, I represented the control room of a sentinel scanning the environment and modulating the level of alertness, the level of vigilance of the system. And so this brain function of vigilance, quiet vigilance regulation, was compatible with the hypothesis of neural efficiency in heartless brain. Then we moved to another brain function in Atlas, the control of equilibrium, of the balance of the body. And the hypothesis was if upright standing reactivity of alpha rims was lower in elite athletes when compared to non-athletes. In other words, if also for the control of balance, there is a neural efficiency of the brain as reflected by lower reactivity of alpha rims during upright standing. And so you see here the persons enrolled for the experiment: 10 elite karate athletes, 10 elite fencing athletes, high level of karate and fencing athletes, and 12 non-athletes. In the experiment, the participants standed on a platform measuring the equilibrium. And in the first condition, they stayed with bipodalic posture, and so they stand upright on the 2 feet. During the most challenging condition, they had to stand up on just one foot. Is the monopodalic posture. And then we computed the alpha activity during the bipodalic posture. And then the changes, the reduction, the reactivity of alpha activity during the monopodalic posture. So we expected that the most challenging monopodalic posture was related to more cortical activation, and so reduction of alpha rings in a monopodalic posture as compared to bipodalic posture. And again, we use the measure of alpha event-related desynchronization, reduction of alpha activity during the task as compared to the resting or a simple condition. And you see in the picture the results at the group level. You see again that the alpha event-related desynchronization, the reduction, percentage reduction of alpha activity was represented in white and red. So negative values, alpha event-related desynchronization reflect the cortical activation. And you see that in this map, in the upper part of the picture, nose up in the map, you see that the cortical activation as revealed by alpha event-related desynchronization was distributed in the parietal and Rolandic central and occipital area. So there was widespread cortical activation as revealed by alpha event-related desynchronization in non-atlas. In the middle map, you see the results for the fencing group. And you see that the red is localized in the posterior cortical regions. And so there was a sort of selectivity of the cortical activation related to the more challenging condition of monopodalic posture. And you see that there is a large area of blue and black showing the increase of alpha activity during monopodalic posture, indicating cortical inhibition. And the same is true for the karate group. You see that karate group is characterized by even more circumscribed cortical activation as revealed by alpha event-related desynchronization in the posterior areas. So this circumscribed selective cortical activation in the posterior regions in Atlas was compatible with the neural efficiency hypothesis, more selective activity, more circumscribed activity in the cerebral cortex in Atlas. So the neural efficiency hypothesis explains the experimental data on EG alpha activity in the task of equilibrium, balance of the body. So we could demonstrate the neural efficiency hypothesis in the brain function of regulation of vigilance, resting state, eyes closed and eyes open, and in the regulation of equilibrium and balance with the body. So we move to the brain function of voluntary movement control, which is clearly very important during sporting activity. And so the hypothesis was, if we have the neural efficiency and the EG alpha activity related to voluntary movements in elite athletes when compared to non-athletes. In this experiment, we enroll 10 elite karate athletes and 12 non-athletes. And you see the experiment. The voluntary movement was performed by hand movement, by the hand. In the first condition, the participants performed voluntary hand movements with the right hand. In the second condition, they performed hand movement with the left hand. In the left part of the picture, you see the representation of the experimental condition. The subjects could perform the unilateral hand movement at self-paced, voluntarily. And so you see, for example, the representation of a right movement at a given time, and then after about 8 seconds, another movement, and so on. So there was an interval between one hand movement and the subsequent. And so we could record EG during the experimental session, and we could measure alpha rins and the amplitude of alpha rins during the periods of resting state condition, and immediately before and during the hand movement. And so we could use the period of resting state some seconds before the movement onset as the level of EG alpha activity during resting condition. Then we could measure the alpha activity 2 seconds, from 2 seconds to the movement onset as the period of the reduction of alpha activity for the preparation of the hand movement. And we call pre-movement period. And then we analyze the EG activity during the 1 second from the movement onset onward as a period of the hand movement. And so you see that we have the computation of alpha event event-related desynchronization during the preparation of the movement period, and then during the movement period. The percentage reduction of alpha activity when compared to the resting period of the EEG recording. Even in this case, the alpha event-related desynchronization is represented in red. And you see that in the maps of the cortical source solutions, nose is up. In the upper part of the picture, we have the results for the right hand movements. In the first row, you have non-atlas results. And you see that it's very clear that in the preparation of a right hand movement, there was a very clear, strong alpha source reactivity in the primary motor and somatosensory areas in the left hemisphere contralateral to the right hand movement. And there was also a very clear source alpha reactivity as a sign of cortical activation in supplementary motor area in the premotor midline. And then during the right hand movement, we have again alpha source reactivity as a sign of cortical activation in the primary motor and somatosensory areas of both hemispheres and the supplementary motor area. So in other words, the non-atlas use the cortical, motor, and somatosensory and premotor, midline premotor areas of both hemispheres for the control of the preparation of a right hand movement and control of the motor performance. When you see the results of the atlas, the karate atlas, you see that the red and the map showing the alpha source reactivity as a cortical activation is more circumscribed when compared to non-atlas. And you see in a clear activation in the primary motor and somatosensory areas in the left hemisphere contralateral to the right hand movement, and some activation also in the other hemisphere, but low in amplitude. So when you compare non-atlas and atlas for alpha source reactivity during the preparation and execution of the movement, you see clearly that there was more selective cortical activation as revealed by alpha event-related desynchronization in atlas, compatible with neural efficiency. You see that the picture is less clear for the left movement, which is the non-dominant hand. So this is a suggestion that when you are using your dominant hand, the system follows the neural efficiency hypothesis much more than when you use the non-dominant hand. And so we could conclude that in the control of hand movements, the heartless brain follows the neural efficiency hypothesis of more selective cortical activation, more control of cortical activation. So even the voluntary movements seem to be prepared and controlled by cerebral cortex following the neural efficiency hypothesis. Then we move to another higher brain function, the visual spatial task. And the scientific question was if reactivity of alpha rins during visual spatial attention task was lower in Hartley atlas when compared to non-atlas, in line with the neural efficiency hypothesis. For this purpose, we enrolled 18 elite air pistol shooters from Italian team and 12 non-atlas without any experience of shooting. During the experiment, we could control the high movements and the movement for triggering the pistol shoot, and we could also record the equilibrium in the stabilometric platform. And you see that we collected this data from a regular competition field, even if during the experiment there was no competition. And you see that we could record EG during the performance of this atlas. In the center of the slide, you see the results at the group level from non-atlas, upper row, and elite atlas, low row. You see that the maps nose is in the lower part of the map. The alpha event-related desynchronization during the movement onset, the trigger of the pistol, when compared to the resting period a few seconds before the trigger movement. And you see that we computed the event-related desynchronization in 3 short periods before the hand movement for triggering the pistol. T3 is 1 second before the movement to trigger the pistol. T2, 1 second before, and T1, another second before. So you see that during these seconds preceding the movement to trigger the pistol, there was event-related desynchronization in alpha rhythms widespread in the cortical model in non-atlas. And you see that the percentage reduction of alpha activity in these preparatory periods when compared to the resting condition affected several cortical areas, especially a few seconds before the trigger of the pistol. But if you now pay attention to the maps in Atlas, you see green and yellow everywhere in the cortical model. And you see in the color scale, in the lower part of the picture, that yellow and green means no alpha event-related desynchronization, no cortical activation during the period preceding the movement to trigger the pistol. And so we concluded that the Atlas, the elite air pistol shooters, were characterized by a very strong neural efficiency, a very strong cortical inhibition in the cerebral cortex, possibly except the specific circuits activating the hand-finger handling the pistol. This means that they were able to isolate the brain during the most delicate period preceding the movement to trigger the pistol. And this means that they were not affected by eventual environmental stimuli and were able to concentrate on the spatial target and the movement to trigger the pistol. So neural efficiency was very clearly shown by our results in elite air pistol shooters. And so we could conclude that these atlas show a behavior of the brain very similar to what expected in a sort of meditation, a sort of Zen meditation to isolate the brain and the person from the external environment, except, of course, of the visual spatial target of this atlas. In a lot of sporting activity, especially in team sporting activity, or when uh, there is a combat with an opponent, for example, karate or fencing um, activities and so on. And so an important higher brain function is the understanding the behavior of other people in order to plan the defense or attacks, for example, or making decision about the best solution. So this is called social cognition. And we tested if the reactivity of alpha rims during these social cognitive activities follows the neural efficiency hypothesis and is lower in atlas than non-atlas. The neurophysiological basis of social cognition was discovered by an Italian group in Parma. They are well-known scientists. The senior scientist is Professor Giacomo Rizzolatti, but there are also other very smart scientists in the same group. And they discovered that within the cerebral cortex, there are some ventral premotor in the frontal lobe and inferior parietal areas deeply involved in social cognition, understanding what another person is doing, or what are the intention of this person in front of me. The original experiments were performed recording the single unit activity in parietal and premotor areas in the monkeys. And in the upper left part of the picture, you see a sketch of the experimental results. You see in the one field of the picture a monkey. The monkey is catching, reaching, grasping a food pellet, a small piece of food from this container, and the movement was the voluntary movement. The action was to take this food pellet and to bring the pellet in the mouth to eat. During this action, a goal-directed action, there was the recording of a single unit activity. And you see that the case that there was a strong single unit activity indicated by these blue vertical lines. The higher the lines, the greater the frequency of action potentials in the recorded neuron in the promotor cortex, the ventral promoter cortex. And you see that during the action, there was a maximum single unit activity when the monkey is grasping the food pellet. In 2, you see that the monkey is grasping the food pellet as in the condition 1, but the monkey put the food pellet in another container. So the action is different. In 1 is I reach, grasp, and bring the small food pellet into my mouth and I eat. In the condition 2, I reach and grasp the small piece of food as in the condition 1, but for another goal, for another intention, to put the food pellet in a container. And you see, when you see the activity of the same neuron, you see that the activation is much lower than in condition 2 when compared to condition 1. And you see the black vertical line, which is the touch moment in which there is the grasping. And you see that the single unit activity, the blue vertical lines, is much weaker in condition 2 than condition 1. In the condition 3, there is the social cognition. While the single neuron activity, the same neuron, is recorded from the monkey, the experimenter performs the same action of condition 1. She reaches the pellet of food and bring the food in the mouth. And you see that the neuron from the monkey's premotor cortex is very active. Just watching the experimenter performing the same action, bring the food into the mouth. So the similarity of the single neuron activity when the monkey is performing the action to bring the food to the mouth, and when the experimenter grasps and the food pellet and brings the pellet of food into the mouth. The similarity of the single neuron activity in this ventral premotor cortex were interpreted as the demonstration that the same ventral premotor neurons are active to perform an action and to give an interpretation of the same action performed by another person. And so the other person is similar to our image in the mirror. We understand what is the intention and the meaning of the action of the other person in front of me, like an image of myself in the mirror. And so for this reason, the group of Palmer called these neurons mirror neurons. And they could also show this behavior of single neurons in the ventral parietal areas. And so this is the basis of the parieto-frontal mirror network for understanding the intention and the meaning of the actions performed by people in front of me. And this circuit, this network was of extreme interest to understand the ability of athletes of combat sporting activities, boxing or fencing or karate, but also other sports in which there is a social interaction and so social cognitive information processing. With this theory on our mind, we performed this experiment on social cognition in athletes, and we enrolled 15 elite rhythmic gymnasts from Italian team and 12 non-athletes. We exploited a special condition in this sport, which is the fact that there are some judgment of the performance of athletes by referees. They watch the performance of the gymnasts and they give a score based on the artistic content, harmonization of the acts of these gymnasts, and so on. In the rhythmic gym, there are some objects, and the team of the athletes throw the objects and catch the objects, and there are some coordinated movements of these athletes during the performance. So there are all the features for a good experiment to test the social interaction in athletes. And so we asked the gymnasts and the control participants to watch videos with the performance of gymnasts, other gymnasts, other teams in international competitions. And so we asked the gymnasts and the non-gymnasts to provide a score like a referee in order to test if they were able to watch the videos to give an interpretation of the athlete performance. Of course, we explain the rules to provide a score to non-gymnasts. And we use the judgments of an expert, the the head of the technical coordination in the Italian Federation of Rhythmic Gymnasts. And you see the results concerning 3 short periods of the performance in the videos. T3 was the period close to the end of the video. The video lasted 8 seconds with the performance of the rhythmic gymnast. T2 was a short period in the middle of the video, and T1 a short period, couple of seconds at the beginning of the video of 8 seconds. In the maps, nose is up. And you see that there is the column of a non-gymnast, and in red, the alpha source reactivity during the video when compared to the alpha activity before the beginning of the video, as a resting baseline for the computation of event-related desynchronization in alpha. And you see that at the beginning of the video, non-gymnasts show the activation of posterior cortical regions in the parietal areas, in the ventral parietal areas, and also midline, including the ventral parietal areas involved in the mirror system, mirror neuron system. In the middle of the video, again, where there is a stable alpha source reactivity in the same regions, and the same is true at the end of the video. When compared the AG source activity in alpha in gymnasts, you see that there was a very clear reduction of alpha source reactivity at the beginning of the video, compatible with neural efficiency hypothesis. And the same is true in the middle of the video. And only at the end of the video, the cortical source reactivity in alpha was similar to non-gymnasts. So it's very clear that at the beginning and in the middle of the video of 8 seconds, the gymnasts are active in the posterior cortical regions and ventral parietal areas in line with neural efficiency hypothesis. We use 40 videos for this experiment. And so we could conclude that there is indeed neural efficiency in the cortical reactivity during the video presentation in gymnasts when compared to non-gymnasts. We repeated the experiment. We repeated the experiment with the elite karate athletes, exploiting a very similar sporting condition, the so-called kata condition in karate. In the kata condition, the athlete performs some attacks or defenses against an imaginary opponent. So he is alone or together with other teammates. Against imaginary opponents, and there is a committee of referees judging the quality of the performance. And the referees use a score to represent the quality of the performance. And so we enrolled 16 elite karate athletes, 16 amateur karate athletes, and 17 non-athletes. And we used the videos of kata condition from an international tournament. And the participants had to watch the videos and give a score for each video. Of course, we provided explanations about the rules to give scores to the kata performances to non-athletes. And again, we have 3 short periods during the videos, lasting 8 seconds. And so you see that the results are very similar to fencing, to gymnasts. And you see that nose up during the video, we have a very clear alpha source reactivity during the first part of the video, the middle part, and the final part. We see that in the elite athletes, there was a very great reduction of alpha source reactivity during the video watching. So a very clear neural efficiency in elite athletes. And in the amateur athletes, there was a very mild reduction of alpha source activity in the beginning part and the middle part, more clear in the final part of the video. So there was an intermediate neural efficiency in the amateur karate athletes. And so we could cross-validate the results of the gymnasts and confirm that also social cognition in the sporting activity, at least in these experimental conditions, was confirmed. And you see here the efficiency, neural efficiency level for for the explanation of the EEG alpha results in the two experiments. Until now, we tested the neural efficiency hypothesis with relatively simple experimental conditions. So we moved to more complex experimental conditions. And so we tested the reactivity of alpha rhythms to visuospatial and somatomotor integration in football players. In the lower part of the picture, you see the results of an experiment in which the football players, 13 football players, they were professional football players, and 8 football amateurs. And so you see that the experiment was based on videos. In the videos, you see that there is the two opponents and 2 bombers. An opponent and one bomber in the left part of the field, and one opponent and one bomber in the right part of the field. And during the video, there was an action towards the goalkeeper, and the bombers try to run far from the opponent in order to increase the distance and allow to better receive the ball from our teammate. And during the video, the participant, the football player or the amateur, had to decide what was the bomber with a greater distance from the opponent. So the best condition to send the ball to the bomber. And so they had to decide if it's better to send the ball to the left bomber or right bomber of the own team. And this was the condition we called football condition. So a virtual simulation of an action in which you have to decide to send the ball to the left bomber or right bomber on the basis of the position of the opponents during the dynamic course of the action. As a control condition, we reuse the same videos with the bombers and opponents, but with another request to the participant during the EEG recording. You see that there is a red cross in the video. In reality, during the video, lasting a few seconds, the red cross changed to blue cross. And so during one video, lasting a few seconds, you have the red cross for most of the time in relation to blue cross. In other videos, the red cross changed to blue cross earlier, and so there was longer time with the blue cross than red cross. And so ideally, the participant has to be right to measure the time of blue cross and the red cross in one video, and to decide the color of the cross being for a longer period. So in other words, there was the same video, the same football action, but the attention of the participant was on the red and changing to blue cross. So a non-spatial feature of the video. So during the football condition, the information processing was focused on the dynamic course of the football action. So this visual spatial and decision making. During the control condition, the focus was on non-spatial feature of the video, the blue and the red cross permanence during the video. And you see that the results were really interesting. Paradoxically, the football players show more alpha event-related desynchronization, more alpha reactivity during the video when compared to the resting condition. So more alpha event-related desynchronization means more cortical activation, in contrast to neural efficiency hypothesis. And you see that the amateurs show less alpha event-related desynchronization, so less cortical activation, paradoxically, in relation to neural efficiency hypothesis when compared to football players. So in the football condition, the complex condition of a dynamic course of football action was related to hyper cortical activation in the visual and visual spatial and the visual motor transformation in football players when compared to amateurs, in contrast to neural efficiency hypothesis. But when we use a control condition in which the focus was on the permanence of red against blue color of the cross, you see that we have the neural efficiency hypothesis in the football players with less event-related desynchronization of alpha activity when compared to amateurs. So this result indicates that specifically for football condition, there was a violation of the neural efficiency hypothesis in football players when compared to control persons. And so there is an interpretation that when the visual stimuli of the sporting activity are very complex, and the athletes cannot use very consolidated neural circuits and task representations, their brains act with a more complex information processing, as revealed by more cortical activation showed by alpha reactivity. Another experiment was performed on experimental condition with integration of visuospatial and the somatomotor balance condition. And we performed an experiment in which the athletes or elite karate athletes, elite fencing athletes, and 12 non-athletes stand up to the stabilometric platform during the EEG recordings, and they had to integrate the visual spatial information processing at eyes open with the maintenance of balance. And so you see that reactivity to eyes open in the balance from eyes closed to eyes open and maintaining the balance on the stabilometric platform was related to alpha source reactivity from eyes closed to eyes open. And you see again the alpha event-related desynchronization represented as white and red. If you see nose up, elite karate athletes, you show that this integration of a balance and eyes open, eyes closed changes were related to a very strong alpha source reactivity in low frequency alpha and high frequency alpha. The same is true for fencing group. Very clear, widespread and strong alpha reactivity from eyes closed to eyes open during maintenance of balance on the stabilometric platform. And when you see non-athletes, you see that the alpha reactivity is less pronounced and is circumscribed in the posterior areas. In other words, when you have to maintain the immobility on the stabilometric platform, and you have to do it with eyes closed and eyes open using visual spatial information of your environment surrounding you. This kind of integration implies more cortical activation in elite athletes when compared to controls. Similarly to football experiment. So no neural efficiency, not less, in this integration of information, visual, somatosensory, vestibular for the equilibrium. Another experiment challenged the neural efficiency hypothesis. The experiment was performed in 12 elite golfers from Italian team. And you see that again, we used our stabilometric platform, the recording of EEG during the sporting performance, and we reproduced the final part of the golf activity. And the put was in a sort of synthetic material, and you see the hole. And this is an instrument that allows us to follow the movements of the tool and the contact with the golf ball, and we could measure the distance of the ball from the hole after the put, or of course the successful puts with the ball into the hole. And at the center of the picture, you see the results, the final results at the group level in these golf players. And we compared the alpha event-related desynchronization as a measure of cortical activity. You see that the red and the white mean the stronger cortical activation as revealed by alpha event-related desynchronization. And you see the difference between the puts with the ball in the hole, successes, or the puts with the ball outside the hole, failures. And you can see that the nose up, that there is more white in the prefrontal areas in relation to successes when compared to failures. And so the statistical map of the difference in alpha event-related desynchronization during successes and failures show a difference, a significant difference in the prefrontal and frontal areas, with more alpha event-related desynchronization as a sign of cortical activation during successes than failures. So more frontal activation immediately before the contact of the tool and the ball. And so means that this prefrontal extra activation was important to integrate multi-giant information, visual spatial information with the position of the hole, and the planning of the multi-giant movements of wrists, arms, and so on. This integration allowed successes in relation to extra frontal alpha reactivity in these golfer players. And so we concluded that the complex decision-making, the football or multi-giant coordination and action with visual and visual spatial information in Atlas brain may be related to a violation of the neural efficiency hypothesis. And so our proposal is that the brain of the Atlas is able to switch from neural efficiency mode when the tasks are relatively under control and relatively simple in relation to the person's experience, but they can switch to hyperactivation and when there is a complex condition with the integration of different modalities in the sensory, somatosensory, visual, and motor, and vestibular systems working together. And so we propose that the model, the neurophysiological model of Atlas brain may follow the neural flexibility of cortical activation in relation to the specific conditions, executive conditions. And so you see that the tentative conclusions is that the neural efficiency is not ever seen in all conditions, and it can be the matter of future studies to test the hypothesis that this kind of neural efficiency or neural flexibility in this Atlas can be a reference, an endpoint of the training programs. And so we publish the results of our experiments in scientific journals in the past years. And these are the members of my group working to these experiments. And these are the European funds for the research of my group in the field of EEG biomarkers in patients with cognitive disorders and Atlas with high performances. Allora, siete vivi?
Sì,
Sì.
presenti.
Ok.